So I'll just finish up with the 8th set of lectures today. I finished the last one with this idea of using Lagrange method followed by Newton's method to find the critical point. And so I'm basically just going to do 2 more examples of that with just slightly more complicated problems. So this one actually builds on one of the questions you just did for homework. So homework 7, we asked why was it difficult to find the critical points of the Lagrangian for this optimization problem. And so what made this one tricky is now the objective function is linear. So it's just coefficient times x1, coefficient times x2, coefficient times x3, coefficient times x4. But the constraints are quadratic. So when I make the Lagrangian, I end up with this lambda 1 times something with quadratic terms in it, and lambda 2 times something with quadratic terms in it. And so when I take the gradient of the Lagrangian, these last two, the 2 elements of this vector that correspond to the constraints that I put into the Lagrangian, they now have quadratic terms in them. So I can't write this as a linear system to solve like I could when I was trying to do the minimum variance portfolio. And so now I need to do this numerically. So I'm going to use Newton's method to solve this. And one sort of annoying thing that I found here is, for some reason, we decide to write the gradient as a row. But generally, when I talk about a function of n variables into n variables, I want to think of that as a column vector. So I'm using this notation just to say I'm taking the transpose of the gradient. And then I'm relabeling that g just so that I'm using the same notation that's in the textbook. And so it's not very pretty. But I can write down the gradient of g. And so all I'm doing here, I'm looking at the first element of my 6-valued function g. And I'm taking the derivative of this with each of the variables. So the variables here are x1, x2, x3, x4, and then lambda 1, and then lambda 2. And then since I have 6 functions, and I'm taking 6 derivatives of each one, I'm going to get a 6 by 6 matrix. And this is the gradient of g. And because all of these functions are continuous, you can kind of also think of it as the Hessian of the Lagrangian. So I got this vector here by taking derivatives of the Lagrangian. And then I got this gradient here by taking derivatives of this thing, which was already a derivative. And so in a sense, these are second derivatives. But I'm trying to find where this function g of x lambda is equal to 0. So I don't want to think of this as a Hessian. I want to think of this as the gradient of g of x lambda. So I can make functions to compute these. They're not particularly pretty, but I made a function g, and all it's doing is evaluating this function here. So you can see the first element is just going to be 3 plus 6 times lambda 2 times x1. Oops, wrong way. And so the first element of this function is just 3 plus 6. And now I'm going to treat this as a function of just one variable, x. So x is a vector with 6 elements. So you just have to kind of remember that the first 4 of them correspond to the x up here, and the elements 5 and 6 correspond to lambda 1 and lambda 2. So x6 is referring to this x here. x6 is lambda 2, and then x1 is actually x1. And so then I have the second element, third element, fourth element, so on, fifth element, sixth element. And all this function's doing is just computing these 6 values, and then it's using this R function, little c, that concatenates them together. So it's just going to return a vector of these 6 values. And then similarly, it's even less pretty, but I can take, so this big matrix down here, Thankfully, it's got a lot of zeros in it, which makes it a bit easier to fill in. So what I'm going to do to write an R function for that, I'm going to call my function dg, so it's for the gradient of this vector-valued function g. It's also going to be a function of the same 6 values that were up here in the function g. So this is a vector with 6 elements. The first 4 correspond to x1, x2, x3, x4 from g, and then element 5 and 6 are lambda 1 and 2 again. And the way it's going to work, I make a matrix called grad using the matrix function. So the syntax here is this is the value that goes into the matrix, and then the second argument is the number of rows, and the third argument is the number of columns. So this command is going to make a 6 by 6 matrix that has only zeros in it. And then I'm just going to go row by row through it. I don't know if this was the best way to do it, but it was the easiest way to make the function fit on the slide. And so I'm just replacing, so in the first instance, row number 1, in the second instance, row number 2, and so on. And so the first one, I'm replacing the first element with 6 times x6, so that would be 6 lambda 2. Then 0, 0, 0, 0, and then the last element is 6 times x1. And so if I pop back, that's just what I wanted to have here, 6 lambda 2, 4 zeros, and then 6 times x1. And so if I didn't make any mistakes, I did the same thing for each of the remaining rows up to 6. And then I want to, when my function finishes, I want to return this 6 by 6 matrix. So I just, on the last line of my function, I just put grad, which is my 6 by 6 matrix, except I filled in all of these entries now. And then I finish my function. So I have a function to compute g, so this vector-valued function g. And then I have a function to compute this matrix-valued gradient of g. And so if I want to use Newton's method, I need a starting point. So I'm going to choose for my starting point 1, negative 1, 1, negative 1, 1, negative 1. Again, no particularly good reason for why I chose this. I actually stole this from the textbook, and this is the starting point he used. So it's not all of me. And then again, the Newton iterations are very easy to write. So I just have to put the matrix here. So this is solving the linear system. So I have what I want to solve is xk plus 1 equals xk minus the inverse of the gradient times the vector-valued function at the point xk. But since I don't want to actually have to compute the inverse of this matrix, I'm just going to set it up as a linear system. This function solves that linear system, and that tells me what my sort of improvement step should be to get from xk to xk plus 1. And then instead of saving all of the xk's along the way, I'm just going to write xk plus 1 into the same piece of memory that was holding the xk. And then this is a for loop, so it says for I in 1 colon 25. So it's just going to repeat this line 25 times. And each time, hopefully, this approximation of the value x, where the function g should be equal to 0, is going to get better and better. And so after 25 iterations, this is the value that I've computed. So the first line, this is on the same scale as the inputs to this function g or to the functions g and dg. So the first 4 correspond to x1, x2, x3, x4. And then the last 2 values correspond to the Lagrange multipliers. So this one is lambda 1, and this one is lambda 2. And so I can write that a little bit more cleanly like this. And so all I know is that this point here is a critical point of the Lagrangian. But what I'd really like to know is it a maximum or a minimum? So have to figure out how we're going to deal with that. So I want to ask the question, does the point xc lambda c, so this is just that vector of 6 values that I had on the previous screen, does this correspond to a minimum or a maximum? And so one thing you might do is just, this is the original function, so the objective function from my optimization problem. And so you can just evaluate that at xc. So this should correspond to one of the constrained minimum or the constrained maximum. And that's equal to 12, but that still doesn't really tell us. So if we were able to find all of the critical points, this would be a way to find the minimum and the maximum. If there were, say, 4 critical points, I could just evaluate this function f at each of the 4 critical points, and I'm going to get 4 values. And one of those, hopefully, is going to be the biggest. Otherwise, there could just be ties. But if one of them is the biggest, then that's going to be the maximum. One of them will be the smallest. That one would be the minimum. But here I only have 1, so I can't do that. And I'm not certain how many critical points this is actually going to have. So my numerical method, it's from a starting point, is going to sort of, you can think of it, if it's looking for a maximum, it's kind of going up to the nearest critical point. If it's finding a minimum, it's going down to the nearest critical point. But once it gets there, it doesn't tell me anything else about how many critical points there are, or I need to try from different starting points or use some other knowledge about the problem to figure out how many critical points there will be. But one thing I can do is try and classify this at least as locally a minimum value or locally a maximum value. And so one of the ways I could try doing that, if I look at this value f of x, so I'm saying for feasible x. And so when I say feasible, this means values of x that satisfy the constraints. And so for feasible x, I can say little f of x is equal to, and now what I've done, I haven't put x sub c here. So I'm saying any feasible value of x, but I'm going to plug in the computed Lagrange multipliers. So I can rewrite out the Lagrangian. So I still have the objective function here, but now I have the computed value of lambda 1 times the first constraint, plus the computed value of lambda 2 times the second constraint. And the reason I'm saying these are equal is when a point x is feasible, this constraint, because I've written it g of x is equal to 0, so for feasible x, this thing that I have highlighted is 0. And also this constraint is equal to 0. So that means capital F of x comma lambda c is just going to be equal to this. So a constrained minimum or maximum is going to, of little f of x, is going to correspond to the minimum and maximum, the unconstrained minimum and maximum of this function f, capital F, x, but with these Lagrange multipliers plugged in. And I already know that x sub c is going to be a critical point of this because that was my condition. That's how I found x sub c. And we had second order conditions. So now this is an unconstrained optimization problem. So we had second order conditions for functions of more than one variable. And that was that x sub c would correspond to a minimum of the objective function if the Hessian is positive definite at x sub c, and it would correspond to a maximum if the Hessian were negative definite at this point x sub c. So positive definite, that just meant that, so this is just going to be a matrix. I take its eigenvalues. Positive definite means all of the eigenvalues are greater than 0. Negative definite means all of the eigenvalues are less than 0. And if you think carefully about what we've done, we actually already have this matrix because it's just this matrix of partial derivatives, and that's just a subset, it's a block of this matrix, the gradient of the function g that I was trying to set equal to 0. So it's actually, let's see, I think I figured out a way to do this. Almost got it. So it's the top left 4x4 block. This is going to be the gradient of this function f evaluated at the point x sub c. And remember, when I wanted to do an eigenvector-eigenvalue decomposition, I was trying to diagonalize a matrix. And so this one is kind of cheating because it's already in a diagonal format. So if you have a diagonal matrix like this, the diagonal entries are the eigenvalues. So in this case, I have everything off the diagonal here is equal to 0, and all of the diagonal entries are less than 0. So this matrix is negative definite, and that tells me that x sub c corresponds to a maximum. And I can go back then and say, for the constrained optimization problem I'm looking at, this point x sub c corresponds to a constrained optimum of the objective function little f of x. So x sub c is a maximum.